today's presentation. Just a few housekeeping items before we start. Please note that there will be time at the end allocated for questions and that the presentation will be available for download in the handout box. Okay, my name is Craig Black and today I'll be conducting today's Snack and Learn webinar for the Helderfontein Pedestrian Bridge. This bridge was provided for our client Century Property Developments, and we enlisted the help of Hoffman Architects to provide architectural renderings like the one that you can see on the screen. A bit of background about myself. I'm a structural engineer from the South Africa WSP office based in Johannesburg, and I'm part of the Civil Bridges and Ground Division. Our team mainly focuses on the design of civil structures such as bridges and culverts. So the agenda for today's presentation, I'll start off on the project locality. I'll speak about the final conditions on the site. I'll then talk about WSP services in this project, the concept design, the workflow process of the project, such as the design, model, and deliverables, some key challenges faced in the project. I'll then touch on the project timeline and then get into some construction photos. And as mentioned, there'll be time for Q&A at the end. So this bridge is located in the Gauteng province of South Africa. Looking a bit closer at the site, the bridge is located in the northern suburbs of Johannesburg, and the bridge spans over the Jukskei River. Looking even closer at the site, the bridge is located to the east of William Nicol Drive, close to the Dainfern Valley area, and the bridge is located within the Helderfontein residential estate. The primary purpose of this bridge is to allow residents to access the school and the area on the eastern side of the river. Looking at the exact bridge location, this location was determined via a site walk with the client. Upon walking around the site, it was noted that there was a local narrowing in the river, with rocky outcrops providing good finding conditions for the bridge. This location was also chosen to allow for a 20-meter span in the river and to provide easy access to the estate. A bit more about the finding conditions for the bridge. Here you can see a geological map of Gauteng. As you can see, the Helderfontein Pedestrian Bridge is located in an area primarily underlain by granite rock. Granite is characterized as being a very hard and tough rock with a compressive strength greater than 200 MPa. With regards to WSP services, we provided structural engineering services consisting of concept design and detailed design. We also conducted the hydrology analysis, including the flood analysis of the river. We assisted with the tender documentation, including tender specification, bill of quantities, as well as procurement of steel contractors. For this, we assisted in obtaining quotes from various steel contractors, and we assisted in providing the client with recommendations on this basis. We then conducted the construction supervision for the entire construction period for this bridge. With regards to the concept design, there were various requirements for the bridge in the beginning. Firstly, the bridge deck would need to be lifted into place over the river. This is due to the fact that formwork in the river would be very challenging and quite expensive. As a result, we opted for a structural steel solution to allow the deck to be craned into place. We also needed to provide the client with a cost-effective solution. The main requirement was to allow easy access for residents of the estate to the school across the river. The final requirement was that existing trees on the eastern side of the river needed to remain in place. As you can see in this Google Earth image on the left-hand side, in order to allow for this, we had to create a localized bend in the bridge to miss all the trees. Zooming in on the right-hand side, you can see the customized sections that we had to create this localized bend. Further to the concept design, there was various options considered for the bridge. Firstly, we considered a truss with varying diagonals. Secondly, we considered a bowed arch truss with a bent top chord. The second option was slightly more expensive. However, upon discussions with the clients, it was the chosen option due to its aesthetic appearance. We then opted for 3 spans of 20 meters. This allowed for the bridge to be above the 1 in 20 flood line. This also allowed for no longitudinal slope of the bridge, which in turn allowed for a smooth transition with a planned pathway on either side of the river. As you can see, and as mentioned, Hoffman Architects provided us with some architectural renderings of the bridge. These were done with the help of some site photos that were taken of the area. These photos were then used to conduct discussions with the clients and plan the way forward. With regards to the workflow process, this slide shows the overview of this. Firstly, the design is conducted, which consists of Procon and reporting. Secondly, we have the model, which consists of Tekla, Civil 3D, and SketchUp. And thirdly, we have the final deliverables, which is in the form of 3D model and 2D drawings. I'll now go into each of these individually. Firstly, with regards to design, this is broken up into two components consisting of the superstructure design, consisting of the bridge deck, which is structural steel, the bridge bearings, as well as anchors into the substructure. Secondly, we have the substructure design consisting of piers, abutments, and dowels into the rock. Various codes and standards were used for the design of this bridge. We have TMH 7 parts 1, 2, and 3, which is the code of practice for the design of highway bridges and culverts in South Africa. We have SANS 10100-1, which is the structural use of concrete for the substructure. And we have SANS 10162, which is the structural use of steel for the superstructure. With regards to the superstructure design, the analysis was done in Procon. This was a 3D frame analysis, as you can see in the bottom right-hand side. Some of the loading that was applied consists of live loads, such as pedestrian loading and flood impacts, dead loads such as the deck and handrails, as well as bracing and stability loading, which is 2% of the compression force in the members, applied laterally. For the superstructure, this deck is classified as a semi-through truss bridge. This implies that the top chord is unbraced, i.e. there's no lateral support to the top chord of the truss. For this design, we consulted the ICE Manual of Bridge Engineering. This provides a theory that states that lateral restraint to the top chord is provided by a series of U-frames. The top chord compression members are considered to behave like columns braced in intervals by elastic springs. Finally, the output of this design calculation is an effective length of the top chord for the compression check. Further to the Procon analysis, the analysis inputs consist of a series of point loads applied to the various nodes of the deck. And the analysis outputs consist of axial forces and reactions which are used for the substructure design. The various members that we used for the structural steel superstructure. For the top and bottom chord, we utilized square hollow sections to allow the top chord to be bent at a radius of 48 meters. For the diagonals, we also used square hollow sections. And for the bracing, we used angle members. Welded connections were used throughout the bridge. This is to create a smooth appearance of the deck, as you can see on the right-hand side. For the bearings, type BAR sliding and rotation bearings were allowed for. We then considered various options for the bridge decking. Firstly, and the preferred option in the beginning was timber decking, either of the form of bullet wood or lunar wood. Upon further discussions with the client, there were some concerns raised with potential future maintenance of this option, resulting in future costs. As a result, we considered two further options. Firstly, we considered aluminium tread plates or fustra plate. And secondly, we considered fiber reinforced plastic grating. Due to constructability and the aesthetic appearance, we opted for fiber reinforced plastic grating. We also considered various options for handrails. On your screen now, you can see 4 options that were considered. Due to simplicity, ease of fabrication, and constructability, we opted for option 1. This provides for a slight taper on the outside of the stanchions. Here you can see the finished product on the right-hand side. With regards to the substructure design, this consists of 2 piers and 2 abutments. We allowed for mass concrete to provide a level surface on the varying granite rock. For this design, we considered flood impact forces. And to mitigate this, we allowed for dowels into the rock. This is in the form of Y20 dowels, 500 mm deep at 500 mm centers. For the pier analysis, we utilized Procon analysis, considering flood impact forces as well as vertical forces from the deck. For the abutment analysis, we also utilize Procon analysis, considering lateral earth pressure as well as vertical loading. Step 2 in the workflow process consists of the model. Firstly, we have the prelim design. SketchUp was used in the concept design phase. This was done to obtain client approval and finalize concept designs. On the left-hand side, you can see the preliminary SketchUp model that was conducted. And on the right-hand side, you can see the embankment protection that was modeled to allow the client to visualize this finished product. The second part of the model process consists of detailed design. Tekla was utilized after the detailed design phase, and this is to produce detailed fabrication drawings. Here you can see two snippets of the Tekla model. From this model, 2D drawings can be outputted from which members can be fabricated. Finally, step 3 of the workflow process consists of the final deliverable. This consists of 2D construction drawings produced in AutoCAD, 2D steel fabrication drawings produced from Tekla, a detailed design report, as well as project specifications that we utilize in the tender process. Some key challenges that we faced in this project. As mentioned before, the bridge had to be designed for flood impact. The bridge crosses over the Jukskei River, which is notoriously known for high flood forces. Here you can see a snippet of the general arrangement drawing of the bridge. As you can see, the 1 in 20 year flood level is about 800 millimeters below the soffit of the deck. In order to mitigate any potential damage due to flood forces, the bridge deck was chemically anchored into the substructure. As you can see, slotted holes were welded to the bridge deck, which were then chemically anchored after the deck was lowered into place. The slotted holes allowed for adequate thermal movement of the deck. In order to anchor the substructure, the bridge bases were dowelled 500 millimeters into the granite rock. In these images, you can see on the left-hand side the pre-drilled holes, and on the right-hand side, you can see the dowels put into place. As you can see, the varying granite level resulted in quite a deep mass concrete layer to create a level platform. One of the challenges faced during construction was a flood event. As you can see in these photos, during the construction of the substructure, a flood event occurred which caused some damage to the scaffolding. You can also see quite a bit of debris flowed down the river, which had to be cleaned after the flood died down. This caused a slight delay in construction. With regards to the project timeline, the construction period was approximately 5 months. The construction of the bridge started at around July 2020. I'll now speak about some construction photos. Firstly, you can see the excavation of the abutments. As you can see, sandbags were utilized and placed around the excavation of the abutment. This is to contain the excavation and prevent any contamination to the river. At the back, you can see netting, which was provided as an environmental exclusion zone. On the right-hand side, you can see the dowels put into place into the granite rock for the abutments. Here you can see some of the reinforcement that was placed for the one abutment. This is prior to closing of the shutters and during one of the inspections on site. This photo shows the construction of the piers. As you can see, and as mentioned, there's quite a large mass concrete layer due to the rapidly varying levels of the granite rock. With regards to the erection of the deck, the span segments were fabricated off-site and transported on the day of erection. There was a crane in place on site to lift the deck segments into place. This is a drone photo taken by the client, which shows the placement of the central deck segment. And finally, you can see the final deck segment being put into place. This slide demonstrates the finished product of the bridge. On the right-hand side, you can see the floor grating as well as the handrails installed. This image shows a recent Google image of the site. As you can see, the bridge is in place, as well as the concrete walkways on the eastern side of the river. Finally, with regards to sustainable development goals, some of the sustainable development goals that apply to the topic of this webinar. Firstly, no poverty with regards to local labor and job creation. Secondly, good health and well-being, as this bridge promotes cyclists and walking in nature. And lastly, quality education, as this bridge provides easy access to the school. Thank you very much for your time. I would like to welcome some questions. Please note that I'll be joined by Johnny Stradham, which is the Technical Director of Civil Bridges and Ground in South Africa. Thank you very much.
Thank you, Craig, for a fantastic presentation. So before moving into the Q&A period, I would like to remind attendees to enter your questions in the question box on the GoToWebinar platform. And also you can download the PDF version of the presentation from the handout box on the dashboard. I will start with the first question. Is the bridge capable of withstanding motorbike or golf cart loading?
Yes, so initially the bridge was only considered for pedestrian loading. There was then a discussion with the client that there may potentially be a need to provide access for golf carts and motorbikes. So as a result, what we had to do was widen the deck slightly to allow access for golf carts. And during detailed design, we allowed for this loading accordingly.
Thank you. In the event of 1 in 100 flood event, will the bridge be overtopped?
Okay, so currently with the current design of the bridge clears the 1 in 20 flood line. However, in the event of a 1 in 100-year flood, the bridge will be overtopped. When this occurs, the bridge will obviously need to be closed. In order to account for this, as mentioned before, we allowed for anchors for the deck into the substructure, as well as anchoring the substructure into the rock itself. The entire bridge for the superstructure and the substructure was designed for this flood impact.
Thank you. What is the expected maximum deflection of the bridge?
So during design, we limited the deflection to about span over 300. So the bridge is within the allowable deflection limits. The maximum deflection is less than 50 mils.
Thank you. There's a question here about gabions. I hope I'm pronouncing it correctly. At what location you had provided the gabions? Not sure if it's...
Yes, so gabions are square boxes filled with, they consist of wire mesh filled with various rocks. And essentially they're used for embankment protection at the approaches of the deck, so up on the embankments to the side of the river. And due to the fact that the 1 in 100-year flood overtops the bridge, this is a potential for causing scour on the embankments on either side of the river. So what we did was we allowed for gabions to be placed around the abutments on both sides of the river. Both abutments have extensive gabions, and this is to protect the embankments from any erosion that might occur during a flood.
Thank you. Let's wait for additional questions to come through. So just let's wait 1 minute more.
Sure.
There's another question here about what is the service life adopted for the bridge in the design?
So generally, we design the bridge for a 1 in 100-year service life.
Perfect, thank you. There is a question about what do you mean by chemically anchored?
So there's a chemical epoxy that's provided by a company or various companies in South Africa. And essentially what happens is there's a hole drilled into the granite, which is slightly larger than the dowel itself. This epoxy is then applied into the hole, and then the dowel is inserted into the hole, and it essentially anchors the dowel into the rock. It's an extremely strong chemical anchor which can withstand extremely high forces.
Thank you. There is a question here about dowels embedded in the river bed bottom. What were the corrosion protection measures adopted?
So essentially the dowels are, they dowelled into the granite, which is, as I mentioned, it's an extremely hard rock. The dowels are then encased in a thick mass concrete layer. They then protrude through the mass concrete layer into the bases of the substructure. So there's actually no potential for corrosion to the dowels, as they are encased in rock and concrete.
Thank you. Another question here, was climate change factors into the hydrotechnical assessment?
So the bridge, essentially with the clearance of the bridge from the riverbed, or from the river water level itself, the bridge has sufficient clearance to cater for rising river levels. So in the event that climate change results in rising river levels, there is sufficient clearance above the weir and above the river itself to cater for this.
Thank you. At the moment, we don't have additional questions. Sorry, there is another question that just came through. How long did the construction of the bridge take? I think you mentioned it at one of the last slides.
Yeah, so it was about 5 months from start to end for the construction of the bridge.
5 months. Perfect, thank you. So we're towards the end of our webinar session. Johnny, let me know if you would like to add anything.
No, thank you, and well presented, Craig. If we can just thank the client again, Century, for this project. Without the client, the project's not possible.
It's true. Thank you for this. So thank you, Craig, and thank you for the client for allowing us to present this great project. And we're at the end of our webinar session. Please feel free to follow up directly with Craig via the contact details shown on the screen. And I would like to thank all attendees for joining today. Thank you very much for your time. Thank you, Craig, for a great presentation.
Thank you, Sharon, and thanks to everybody that joined. Thank you very much.